And our next presenter is Jussi Poikonen, who will introduce artificial intelligence in maritime logistics. Welcome, Jussi.
Thank you, Justina. Very happy to be here today. I'd like to talk to you a little bit about the work that we do at Awake.AI on predictive analytics, machine learning, and AI in general. To get started, I want to kind of define the basic business motivation behind our work and to put it really simply in a very abstract level into a nutshell. Basically, we are aiming to improve the planning in maritime logistics, and basically successful planning requires information on where things are now and the ability to estimate where things will be in the future. So we speak about situational awareness, situational understanding, and of course optimization of processes. Now, currently in the maritime logistics chain, this kind of information is generally not very well available, so that it would be always accurate, up to date, and somehow cost effective, that is kind of automatically produced instead of having many people monitoring all processes. So this is a kind of simple problem definition, but of course involves a lot of technical work on many different parts of the logistics chain. Now, the basic principles for us, how we develop analytics at Awake, are shown here. These are automation, integration, and scalability. By automation, we mean basically that processes such as model training, model deployment, and sharing of predictions are orchestrated. All information that we produce should be always available where it's needed and beneficial, and not, for example, just curated by humans at specific times. By integration, I mean that we are not developing analytics as a standalone feature. Analytics should be a part of the whole platform, the system, and provide enhanced information value to other services. Now, if you think about automation and integration together, basically the idea is that we are not selling, for example, predictions for 5 cents. We are not selling numbers that you would buy separately. We are selling enhanced information, which is automatically used to improve, for example, berth planning or other operations planning. Now, the third guiding principle is scalability. We want to develop models that scale both computationally and geographically, can apply these easily over the whole world, and enable these beneficial network effects. So when our platform expands to new ports, we can get better information by joining, for example, the scheduling predictions and monitoring that we have from different places. And I will show during this presentation a practical example of this kind of effect. During this presentation, I'll be going through on a quite high level the analytics models that we are developing. Basically, we can divide them into this kind of categories. So this kind of flows from vessels approaching the port to cargo operations to looking at resources in the port. So we'll be looking at destination prediction models, predicting arrival times for vessels, cargo operations, and resource tracking. And of course, we have many kind of subcomponents that are used to make these kind of predictions, and we use a lot of data sources in these models. And of course, we won't go into the very technical level, but I hope to give you at least an idea of what we are doing and the approaches and the data that we use to get there. So we start with navigation models. navigation modeling and prediction is of course very important in the maritime domain, and we do that on a very wide scope, basically from physical modeling of hydrodynamics, aerodynamics affecting a vessel's movement, which is used, for example, to simulate predictive control methods for autonomous vessels, to predicting and analyzing port call sequences internationally on a European level. So we also kind of try to understand flows of cargo, flows of vessels between ports in Europe. But in this presentation, I'd like to focus on somewhere between these extremes, and that is how we predict the arrival times of vessels approaching a given set of ports right now. Now, looking at vessel movements and arrival prediction, basically the main data source is of course AIS data. Perhaps it's good at this point to kind of briefly define and discuss what this means. AIS is the automatic identification system, which is mandatory for large commercial vessels to use. They broadcast these AIS messages frequently, and they contain the ship's locations, speed, heading, all kinds of dynamic information, and also information about the voyage, like the voyage destination, the estimated time of arrival, and so on. So basically, on paper, this AIS data, the AIS system, is just what we need to predict vessel arrivals, to understand where vessels are moving. Unfortunately, in practice, the system is, let's say, not used optimally. And that's basically due to the non-structured nature of the AIS field. So basically, many information fields in the AIS messages are input by humans by just typing on a keyboard, probably, and the information is generally not very reliable. For example, if we look at the AIS destination messages over European port calls, here in this statistic, we have been looking at about 900,000 European port calls in the beginning of this year. You can see that looking at all countries, approximately 9% of voyages, the vessels are completely missing destination information. And this is strangely enough quite dependent also on the country where the vessel is headed. So France is kind of leading the way here for some reason. But still, I mean, you could argue that in many countries this is a minor problem, having missing destinations in AIS. But the problem is that even when you do have the AIS destination information, the destination string itself can be pretty much whatever. So an example of that is shown here. These are the reported destinations in AIS messages for vessels arriving in Hamburg, whose low code is DHAM. So basically, from this larger part of the image, you can see that you can see all kinds of reports for the destination, and for kind of machine readability, this is of course not a very good case. You can see a kind of wide shot of the whole example in the right-hand side, and you can see that there are really a lot of variance in these reported destinations. So this requires already some non-trivial analytics to kind of decide based on these kind of destination reports where these ships actually are going. Now, same goes for the AIS estimated time of arrival messages. Here again, statistics from the same data set. Here the x-axis is showing the error in estimated time of arrival as reported in the AIS system. And you can see that especially for cargo vessels, there is a lot of variance in these ETA messages. So you can easily have tens of hours, even hundreds of hours of error in this destination announcements. Time of arrival messages. So we need to do something to make this data better, and we can do that with, for example, machine learning models. So the ultimate goal here is to predict when vessels will be arriving to a set of ports that we are interested in. And to do that, we need to, of course, monitor all of the ships, in this case in European waters. We analyze the AIS messages and try to detect first ships who are headed to these ports of interest. And to help in predicting the arrival times, we also predict the trajectories, the routes that these vessels will take to get to these destinations. For example, in this example image, we are looking at routes taken by vessels to Tornio during January to February 2020. You can actually take a closer look at this data. So looking at the kind of farthest starting points, we have several voyages starting in the Netherlands. And here the yellow dots are the AIS location messages. The yellow texts are the AIS destination reports. The blue texts are the predictions for the destination made by our models. And the blue dots are the voyage trajectory predictions made by our models. So you can see already here we have a lot of different messages for Tornio. For example, here is Tornio anchorage, Tornio area, Tornio buoy, Tornio arm, whatever, but these are all correctly identified as voyages going to Tornio. And if we quickly just trace these voyages, maybe zooming back a little, we can see that also the trajectory predictions are very realistic for all of these cases. Now, this is a very good starting point for predicting then the arrival times. We can be pretty confident that we can catch the vessels that are actually coming to a given port. And we can be quite confident that we know approximately how long the actual voyage will be in distance. All right, let's get back to the presentation. And of course, this is a computationally challenging task also, as we are doing this kind of analysis for all vessels in Europe. That's maybe of the order of 100,000 vessels, each transmitting AIS messages maybe every few minutes on average. Now, for the detected vessels, we would then do ETA prediction. Here is an animation of that. Let me just pause this to explain. So what you are seeing here are these kind of time checkpoints along the trajectory. So we are predicting from the first point, the farthest point from the destination. And I have plotted here these kind of points where the vessel will be at approximately 3-hour intervals into the future. And we do this, of course, constantly along the vessel's voyage and get better and better approximations as we learn, for example, about the vessel's speed profile and how the voyage is progressing. In this case, the actual arrival time of the vessel was on the 3rd of February at around 3 o'clock, and the voyage duration, total duration, is approximately 4 days. So already close to the start of the voyage, the prediction is quite okay, and it gets better all the time as the vessel approaches Tornio. So this is about maybe 2 or 3 days away, and it's now already within, let's say, minutes of the actual arrival time. And now we are getting to the last day of the voyage. So this is 4 days condensed into about 30 seconds. But basically, this is the kind of time of arrival predictions we are doing for all vessels approaching the set of target ports. And for us, that target set is, let's say, many major ports in the Baltic Sea and around Europe. So this is, we're doing this for tens of ports currently. Now, of course, it's interesting to look at the kind of accuracy and what kind of models we can use for this. So, of course, there are kind of many different approaches you can use for this, estimating the speed of the vessel during the voyage and the eventual arrival time. So here are kind of two extremes. On the x-axis here, you see the actual time of prediction for this voyage animation that I just showed. So this is 4 days. And on the vertical axis, you can see the prediction error to the destination in hours. So the red curve here is this kind of slowly adaptive model, which gives a very, let's say, stable approximation for the arrival time. So 4 days from the port, we can see that the error is about 4 hours. And 3 days from port, it is under 2 hours. And from about 2 days to port, we are persistently under 1 hour of error in the estimation. Then again, we can use this kind of quickly adaptive models shown in blue, which have the advantage that you can basically get very good estimations quicker, but these are more kind of volatile. So if the vessel does something kind of abnormal during the voyage, then you can have parts where the prediction estimates are not so good. So of course, to get the best results, we typically combine these kind of different modeling approaches, for example, to some kind of ensemble model. But the point is that for operations planning, it is possible to get very good and constantly improving estimates for the vessel travel times. All right. So we looked at basically the vessel prediction part, destination prediction, time of arrival prediction. If we want to model the whole port call, then the next thing we should understand is the delays at berth, which are like pre-operations delays, then of course loading and unloading delays or delays after that. And if we can model these, then we can actually predict the whole port call duration. Well, let's look at these cargo operations models. Sorry. So basically, we can have two kinds of models. We can have models which are applied before the operations even begin. So for example, for berth planning, it's good to be able to approximate for a given vessel already before it arrives to port how long the operations will last. So here's one example of that kind of data. In the horizontal axis, we have here the cargo amount for an example port where they do loading operations. And on the vertical axis, we have the corresponding loading times. And we have applied this kind of time series models, machine learning models to this data. And the colored points here are approximations provided by our model, and the gray points are kind of true times. And it's interesting to look at this basically analysis of the feature importance. So what factors in the data that we have actually affect these predictions most? So of course, it's kind of natural that the cargo amount is very important. And you can see that there is kind of linear dependency between the cargo amount and the loading time. but still we can see also a lot of this nonlinear effect. So there are a lot of outliers and this kind of, let's say, strange cases here. So the question is, can we understand those? And it seems that it is also very beneficial to, for example, know the vessel history, which vessel is actually we are looking at, the starting hour, starting weekday of the work, and for example, the berth where these operations are done. They are also called jetties, by the way, in this legend. So we use all available data that we have to make these kind of predictions. And basically, in this case, I don't think we have all the data to perfectly model this, but we can do pretty good approximations with this kind of information. In addition to this kind of predictions, we can also make constantly improving predictions as the loading operations or unloading operations are progressing. So typically we would have data looking something like this, where along time on the horizontal axis, we get, for example, container loading events. So here on the vertical axis, you can see that the cumulative number of loaded containers increases towards the total amount in this job. And then we would typically like to have information, for example, on the break times when people are not working. So that's illustrated here with the red boxes. And if we have this kind of information already, we can do pretty good approximations on the completion times, which of course improve as the work goes on. We would make this kind of dynamic learning model, which tries to all the time adapt to how the work is actually progressing. All right, now that we have discussed navigation models and operations models at berth, it's interesting to look at this kind of case study for how we can actually apply these kind of models to do port call optimization. How can we enhance berth planning with these kind of models? So in this case study, we'll be looking at one port in Finland and specifically one berth in that port during 1 week. Now, let's say that from berth planning, we know that 3 vessels are going to visit this berth during this week. They are arriving from Oulu, Kokkola, and Stockholm. And we know that the berth is reserved for some time in the beginning of the week. So here it is 3 days. At the beginning, the ships will not be able to come to the berth. Now, we would like to understand beforehand, of course, as far as possible, how things will actually play out. Now, if we apply the models that I showed in the previous slides, we can, of course, get some kind of prediction or simulation for how this week will progress. Now, again, on the horizontal axis, you have time, so it is from February 7 to February 14. And here on the vertical axis, you have distance from this port. So we can see that on February 6, I think, this ship, which we call Bardo, departs from Oulu. And we can predict that it arrives to this port around February 9. Now, as the berth is occupied, the ship has to stay at anchor close to the port. So that is indicated here as this kind of horizontal line where the distance does not decrease. And when the berth is freed, the ship goes to the berth, and we predict the duration of the operations. So you can see that here we actually divide the berth time to 3 segments. It's this kind of pre-operations time, then the loading operation, and the post-operations time. And we have different time series models for each of these. We apply these consecutively and have an approximation on when the ship will depart. So of course, the last point here in blue is the departure time, estimated departure time for this vessel. Now we do the same prediction for Rocky, who departs from Kokkola. And we can see that the berth is still occupied approximately for 1 day when Rocky arrives to this target port. So she also has to stay at anchor for approximately 1 day. That's our prediction. Then Donald departs from Stockholm and arrives just a little bit later than Rocky, according to our prediction. And she will have to wait at anchor now for almost 2 days. Then finally, we predict that Donald will depart this port a little bit after well, let's say a little bit before February 14th, and then the berth will be free. Now, this is of course not just a PowerPoint exercise. This is based on real visits, so it's interesting to see what the actual events were. So these are from historical data, how things went. And if we look at the predictions, the simulation versus the reality, we can see that these models provided very good estimates for the event timings. Now, of course, this is all done basically from the point of view of February 7th, so 1 week before everything. In production setting, we would of course do these kind of predictions continuously. So as we get more information on the locations of these vessels and how the operations are predicting, we can further improve these predictions. But already before everything, we can get very nice predictions. Now, what can we do with this? There are many things, but for example, here we could have said to the vessels that there's no point coming to wait at anchor. You can sail slower. For example, here Bordeaux could have sailed at 24% reduced speed, reducing time at anchor almost 19 hours. Rocky could have sailed 36.4% slower with 25.8 hours less waiting time at anchor. And maybe Donald could have decided, I don't want to sail this slowly from Stockholm to wherever they are going. So they could have departed, for example, almost 2 days later, maybe doing something else before coming to this target port. Now, this is all kind of, these are things that you can do, and reducing the sailing speed, of course, has potential in reducing fuel costs, emissions, and so on. But I think that the point is that when you can predict how things go accurately, then you at least have a choice in matters. You can decide to do whatever. If you want to, you can come and wait at anchor, but maybe there's something more intelligent that you can do. And this is the kind of main benefit of predictability. Of course, one other thing is here we can accurately predict the departure times for each of these vessels. And that, of course, will affect their next port call. So we can see that all of these vessels are about at least 1 day late of their original schedules in some sense, as they had to wait at anchor each for at least 1 day. So we could propagate this information to the next port. So we can then simulate if they depart this XXX at these times, then they will probably arrive in the next destinations a bit late also. So this is the kind of network effect that we get from applying this in multiple ports at the same time. All right, so we had an overview of this kind of what we can do with predictions at sea, predictions at land. And this was all kind of time series analysis. So as the last part of this presentation, I'd like to talk about tracking cargo at port. And this is rather different case also from the perspective of like analytics work. So we have been developing computer vision models for basically monitoring large cargo areas. And this kind of work benefits a lot from the modern neural network-based computer vision models, which are nowadays very good for example, detecting objects, classifying objects, and doing things like semantic segmentation, where you can actually divide portions of image data according to what is actually in the scene. So this doesn't apply just to this kind of, for example, cars, but you could also segment, for example, bulk and many kinds of things in areas. Now, to apply these kind of models, what we would typically do is model the camera systems in the port and see if they are already kind of applicable for this kind of monitoring. So ports typically have surveillance cameras which are not optimally used for this kind of analytics, and we can really do a lot if we get access to this image data and optimize a little bit, for example, the positions of the cameras and the coverage towards the target area. And we have done work on providing, for example, recommendations where to place cameras for this kind of analytics and maybe other sensors also. And when we have this, when we have modeled the camera systems, we know the kind of geometries related to this imagery, then we can, of course, map all of the detections that we get also to, well, basically any kind of geodata. So we can visualize, for example, in this kind of 2D maps, what we have in this area. And ultimately, typical use cases are, for example, this kind of object detection and tracking, where a customer would like to monitor, for example, the utilization of an area which is reserved for a certain kind of cargo. We can also try to classify different types of cargo. Here it would be, for example, different types of cars. And combining these computer vision models with time series analysis, we would like to do automated tracking of, for example, area usage per cargo unit, maybe track how long a specific cargo item, like a car here, has stayed in this lot, and of course can do real-time analytics in showing these kind of statistics for the area. For example, here we have done some time series analysis where we kind of indicate the positions where cars have exited this lot with red X's, and the positions where new cars have arrived with blue markers. And if we would have some place where the car has just changed to something else during our images, those are marked with green, although I don't think there are any here. So this is a very kind of interesting possibility for many ports, and as I said, can be applied to many kinds of cargo types. Cars are nice in the sense that there is a lot of open training data available for training, for example, car detection models. But of course, this kind of work can be done with any kind of visual content. So we just need to annotate the image sets for the customer's cargo, and then we can develop this kind of models. All right, that was a brief overview into the analytics work done at Awake.AI. I hope this was interesting for you, and I would be happy to answer any questions you might have at the end of this webinar. Thank you.